Introducing you. Hello, everyone. Welcome to MACSMIN 2025. It's a great pleasure to introduce Professor Gregory McColm from University of South Florida, who will talk about using category theory to describe complex structures. Please, Greg.
Okay, thank you for coming this afternoon or morning or evening, depending on where on the planet you are. This is a project that Bertold Sturger and I have been working on ever since we were at a conference, and we had a chat with Massimo Nespolo, and because he and Bertold had written a paper on the groupoid interpretation of category theory, and they had published, I believe, in ACTA. And so Massimo more or less told us that we should start working on category theory and hopefully write some kind of book on how to start using it. So this is sort of the first report on our project. So categories. Category theory can be used to look at a structure. This was the original purpose of category theory, and this is what Bertold and I are trying to do. But category theory has been used for just about everything since then. So here's the original version. There on the left is Samuel Eilenberg and Saunders MacLean. And they were interested in dealing with groups acting on topological spaces, which is another way of saying they were expanding on the work of Henri Poincaré, who is on the right. And Poincaré's fingerprints can be found all over crystallography. In fact, Poincaré's fingerprints can be found all over the natural sciences. But we're talking about something that was developed after Poincaré died, but it grew out of his work. So this is the vision I've been selling in the category theory class that I am teaching this semester. And that is, you may have heard that mathematics, the foundation of mathematics is set theory. However, no one actually uses set theory, they just stand on it. What they increasingly use is category theory. And I call category theory the roof because it is started off in topology, but now it's increasingly everywhere. And it provides a vocabulary for people anywhere in mathematics to talk about their mathematical topics and other people understand them. And this is important in mathematics. Mathematics, according to the American Math Society, is chopped into about 6,000 subfields. And you have different vocabularies in each. And one consequence is that category theory is something that they all understand, at least at the moment. I mean, category theory itself is fragmenting. But meanwhile, category theory is invading other areas. It started off by invading computer science, and a lot of the category theory for layman books are actually written for computer scientists. So Bertold and I are interested in category theory for crystallographers. So we are actually taking a slightly different approach from the mainstream of the subject. But our interest is one that goes back to Poincaré. There are 25 gazillion structures listed in topos. There are 37 zillion structures listed in the Cambridge Structure Database. I don't keep up with how many structures are listed in them. How are you going to organize these things? We want some kind of Linnaean project to understand these things. And so category theory may provide what we want to do. So the first thing to do is to understand what a category is, and I'm going to go a little bit slowly, and I invite anyone to stop and wave their hand because Bertold warned me that this is rather abstract, and I want to make sure that people have at least some idea of what's going on. Okay, let's go all the way back to Eilenberg-MacLane, talk about a critter that we all know about. These are groups. And so what you start off with is the class of all of their groups and the class of all of their homomorphisms. So this is all the groups and all the homomorphisms. And then we have a function that assigns to every one of these homomorphisms its domain. So every single homomorphism is going to map one group to either itself or to another group. And the other group that it maps to is the codomain. So every single homomorphism is going to have a domain and code. This actually should be a G. I apologize for that. So it's a map from H to G. And then we actually can compose these homomorphisms. So if G maps into the same group that is the domain of F, you can compose them. And those are the basic things that we have in a category. And we have some restrictions, but these are the restrictions we're all used to. First of all, the binary operator is associative. So if you compose 3 homomorphisms in a row, it doesn't matter what order you compose them. And second of all, you want an identity homomorphism. And in category theory, you characterize that by saying, well, the identity is the homomorphism, which if you compose it with anything else, produces that anything else. Doesn't matter what side you compose it with. The identity composes with something and that produces something else. So that's all what a category is. Okay, now one thing about category theory, and this is what intimidates people, is that we're all used to being sort of sloppy and, if it fits, it works, blah, 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 blah. The category theory is unforgiving. You have to be precise what you're talking about. And this is why I'm turning to graphs. Graph theory is used an awful lot in crystallography. But when you are going to talk about the category of graphs, you have to be precise about what you're talking about. Let me give you an example. One way of thinking of a graph is a graph has a bunch of vertices and a bunch of edges and has incidence relation. So you have the vertices, the edges, and the incidence relation says this edge has this vertex as one of its endpoints. So this is one way of thinking of a graph. So here's some graphs. So you have, here's an edge, it has endpoint, endpoint. Here's an edge, endpoint, endpoint. They can have the same endpoints, but they might still be different edges. And you can have an edge that has both endpoints be the same point. That's a loop. So this is one way of representing graphs. And then we have graph homomorphisms. And with this particular model, what you can do is you can map the vertices and then the edges tail along. So this vertex is mapped here. This vertex is mapped here. So this edge is going to be mapped into this one here. Notice this is not an onto map, but this does have this particular homomorphism. This is the domain and this is the codomain. So this is the kind of graph and graph homomorphism we want to use. But now here's something that is often done in crystallography. We want to take this graph and we want to map these vertices onto this graph in a homomorphism. The problem is this edge right here. If I map this edge to this edge and this edge to this edge, and therefore these two vertices to this edge, where does this edge go? And category theory is going to ask that question. You actually have to use a different model for graphs. So this is the other model that is often used in crystallography, which is you're pretending that this vertex is actually a point, this vertex is actually a point, and this edge is actually a line segment consisting of uncountably many points. And you're going to continuously map all these points to points. So this vertex is a point mapped to this point. These two vertices are points mapped to this point, and all of these points on these line segments are mapped to this line segment. So this is a distinct model, and we have a different category of graphs. They can be articulated. I'm not going to talk about articulation between categories today, but that's actually a major part of the category business. But you do have to be careful about what model you are using now. So this is the first measure, first takeaway from this category theory talk, which is categories will force you to be honest. No more slouching around saying this will fit or anything like that. You actually have to be precise about what you're doing.
Greg,
Yes.
could I ask a question? So the top left vertex, the black one, is it mapped to the green vertex on the right?
Yeah, this vertex maps to this vertex. These two vertices both map to this vertex.
Uh,
So this edge is mapped, both these edges are mapped to this edge. And
uh-huh.
now the category theory question is, what happens to this edge?
I'm asking about the top left black vertex.
Uh,
Top left in the square.
oh yeah, that's also mapped here.
So black to green.
Oh, so this is black to green. Yeah, you are absolutely right, because this and this also should be green. Thank you.
Okay.
I goofed. Thank you. Okay. So you have to be careful. And category theory, yeah, I tend to make a lot of mistakes for someone of my ability, according to my thesis director. I decided to take that as a compliment, but you do have to watch me. Okay, so we've seen some categories, and here is the very abstract definition. And my recommendation is think of graphs. So a category is you have a class of objects. Think of groups or graphs. And then you have a collection of things called morphisms. Think of homomorphisms. Today, all of these things are going to be functions from objects to objects. But category theory has gone all kinds of places, and they don't necessarily have to be functions in all contexts. They will be today. Then we have a function that assigns to every morphism a domain. So think of the domain as your function. And then it also assigns to every single morphism a codomain. Think of where that function maps things to. It's often in lower division math courses. This is what's called the range. Where is this thing going? It's not the image, it's the where it's going. So this is typically called the codomain. And then we have our composition operator. And again, it only works if you can actually compose the morphisms. That is, the one morphism is mapping into a codomain, which has to be the same as the domain of the next morphism. So this is composition, and it has to satisfy the same criteria we saw before. Namely, you can compose two morphisms only if the codomain of the first one is the same as the domain of the second one. And secondly, every single object has an identity morphism. So on graphs, this is the identity homomorphism. On groups, this is the identity homomorphism. And finally, morphisms are associative. So it doesn't matter what order you compose these things. So that's all that a category is. Sounds deceptively simple. Okay, now today we're interested in hierarchies. This is one way of using category theory. Very strangely enough, it's not being used that way in ecology. Ecology hierarchy was very big in the 1990s, but now hierarchy is not as big anymore. But it is showing up. The computer scientists do this all over the place. But one place where a biological hierarchy is turning up is in neurology, and consequently in models of artificial intelligence. But today we're interested in topology and geometric structures representing materials. Okay, so remember we're thinking of morphisms as functions, and there's two very kinds of important functions that show up a lot. One are one-to-one functions. So this is what they look like. Here's the domain, here's the codomain. Every single element in the domain is mapped to its own element in the codomain. There's some elements in the codomain that don't have anything mapped into it. That's not a problem. All that's required is that every single element in the domain is mapped to its own element in the codomain. Now, after you complete calculus, many places, if you're going to be major in mathematics, you take a course. Essentially, it's called a number of things, but it's essentially how to prove stuff. And one thing they tell you is that onto functions have a nice property. If you compose a one-to-one function, if you compose a one-to-one function on the right with two other functions, and the result is the same. So f composed with g is the same as f composed with h. That will happen only if g equals h. And that's because g is feeding into a one-to-one function, h is feeding into a one-to-one function, so you don't have anything mapped. You don't have any situation where two things are mapped to the same place. So that means that g and h must actually be the same function. And so you now have an algebraic representation of being one-to-one, and you call that monic. The other special kind of function is an onto function. So here, I have actually turned the domains around, and that's plot material, by the way. Every single element in the domain is mapped to something in the codomain, but more to the point, you're onto if every single element in the codomain comes to at least one thing from the domain. You can have several things mapped. E and C are both mapped into 5. But the point is that everything in the codomain has to come to something from the domain. And this is something called onto. And there is an algebraic representation as well. If you take that how to prove classes, they will show you that now you're composing on the left. If you have something G composed with F and H composed with F, and they are the same thing, that implies that G equals H. And this is, loosely speaking, because everything in the domain of G comes from something in F. Everything in the domain of H comes from something from F. And so that forces G and H to be the same thing. So if you have a function that satisfies this onto-ness notion, you call it epic. And now here's the curious thing. You notice that this picture was the reverse of this picture here in a sense. And that actually shows up here. A function is called monic if whenever you are feeding into it, two functions feeding into it and then getting f, and the compositions are the same, that means you call it monic. Now, suppose you reverse the arrows, and yeah, I know I'm switching A's and B's here, but you're having a picture in which the arrows are reversed, and that's called epic. So you say that being monic and being epic are duals, and these duals show up an awful lot in category theory. And if I actually get there, we'll see how the duals show up in crystallography as well. Okay, now this is one of the things we want to do. We want to build a crystal, and in fact, you can build up any kind of material, sort of like putting together things with Legos. And I remember one of the recent Nobel Prizes, they said that you're building molecules by putting together Legos. And crystallography will allow you to do that. And they use these things. Okay, so a source is when you have a single object and you have a whole bunch of morphisms that have that object as its domain. So you have a whole bunch of these morphisms going out, and they might go to different objects, or you might have several morphisms going to the same object. And so this is going to be an object that is used in creating these other and subsequently bigger objects out here. And what we will see later down the road is the dual of this. You can have a whole bunch of morphisms coming in. And that means that all of these objects out here have to be somehow the result of mapping things into this object. And so that imposes conditions on this codomain object right here. And these constructions are duals of each other. So let's look at the kind of thing that we can do with sinks and sources. Let's start off with a source construction. So I have a Lego here, well, puzzle piece here, and another puzzle piece here. And I want to put them together to make this thing here. And I want it to get precisely this thing here. I can put these together inside of a bigger puzzle here, but the point is that when I put these things together here, this can be mapped into any other structure in which I can put these together. This is what a coproduct is. A coproduct is when I can take two things or more than two things, but let's stick to two things together to get a single thing such that any other thing that these two things can be put together in, it will also contain this minimally put together thing. So that's the idea of coproducts. And this is an example of something called a commutative diagram. We have already seen commutative diagrams. Commutative diagrams means when you compose this and this, you actually get something that is the composition. This composed with this is the composition of the two. This composed with this is the composition of the two. And that means, now to the point, when I compose this and this, I get the same thing as when I compose this and this. That means that's what we mean by commutative diagram. Now, coproduct can allow you to do things like take one view of a periodic structure and another view of a periodic structure and put it together in something like this. So we can combine different structures. If we have a motif and a lattice, something like that, we can put them together and we get a bigger picture of the structure. Now, this coproducts work only if the union is, if these are disjoint, but there is a way to put them together if the two things you're putting together are not disjoint, but I'm not going to talk about that today. Now, coproduct has a dual, and that's actually called product. If you frequently in category theory, if you have a something and then you look at the dual of that something, you call it the co of that something. So people came up with products first, and they came up with these coproducts. So what is a coproduct? Well, again, it's just reversing the arrow. So I have this structure here, and it has two projections. You can project all of the squares to this square, all of the stars to this star, all of the hexagons to this hexagon, and all of this very pointy star to this pointy star. Or you could project all the red things to this red thing, all the blue things to this blue one, all the yellow ones to the yellow, all the brown ones to the brown. And this is the specific thing that is the product of these two, because if there's anything else that projects in these directions, it will also project over here. So that is what we mean by a product. It is the minimal thing that will project in these two directions. And there are certain limitations of the product and coproduct construction. So for instance, suppose I wanted to take a product of these two. And so I have to decide, again, what are your morphisms? So I am using essentially the incidence graph, the combinatorial incidence graph category of graphs. And my product is going to wind up being Cartesian product. And the result is that the Cartesian product of these two things winds up looking like this. Now, if you wanted some other kind of product, you would have this other kind of thing to be the product. You would have to use something other than the product construction. But this is what you would get if you tried multiplying these two together using Cartesian products. Suppose we wanted something else, though. Suppose we also want to have symmetries built into this. I mean, this thing has a whole bunch of symmetries in it. This has symmetries in it. And these symmetries are not reflected in this bunch of morphisms. We want to have the whole idea in category is that your morphisms capture what your structures represent. So what Berthold and I did is we got out this old book by Grunbaum and Shepard. And those of you who've seen this, it's a wonderful book called Patterns. And the idea is that you can have the word you use is motif. Motif essentially is represented in manifestations that recur throughout a structure. So and Grunbaum and Shepard, they call those images, the motif fragments. So we decided to call them that. So we're actually moving into something called hierarchy theory. Hierarchy theory well, people have been talking about hierarchies for a very long time, but it all goes back to a work by Arthur Koestler called The Ghost in the Machine, and it was picked up by a whole bunch of biologists, economists, system scientists. As I said, the biologists have drifted away from hierarchy theory, but I'm convinced that they're coming back. But the idea of a hierarchy is that you have these holons, and a holon could be, you could have a cell and it's part of a tissue, and that tissue is part of an organ, and that organ is part of an organ system, which is part of an organism, which is part of a social group, and so on up. That's the way the ecologists thought of hierarchies. We're pattern people, so we're interested in subatomic particles being in an atom, which is in a molecular building block, and which is in a motif, which is, and so on up. And so we're thinking of hierarchies in this way. And so we drag out of category theory the notion of a subobject. And a subobject, you have an object here, and then you have a morphism that maps, you have a bigger object right here, and this thing is monic. You're supposed to think of this as a one-to-one function, and it's mapping this motif into this particular fragment. This is the term in Grunbaum and Shepard. This is the motif, and it's being mapped into this fragment right here. It's also being mapped to this fragment right here, into this fragment right here. That's what it's doing. But the thing is, this motif has internal symmetries, which we would like to represent in the category. And this also has symmetries that we'd like to represent in the category. And not only category theorists, crystallographers and art historians both would like to say that there are symmetries in this thing that are not reflected over here. So we would like to be able to talk about all these symmetries, either preserved or broken. So what we do is we start off with fragments. A fragment is going to be a whole collection of monics, every single one-to-one function that maps this object into this object. They are collectively the fragment. And then there's another fragment, all of the one-to-one functions that map this thing into this thing. And moreover, we would like to have all of the symmetries of this big object, this big pattern. Pattern is the word used in Grunbaum and Shepard. We would like to have all of the symmetries of this pattern be reflected in this motif. So what we say is that this has reflection, 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 and they are all reflected inside of here. Rotations all reflected inside of here. However, there are some symmetries in here, like rotation, the eightfold rotation in this motif, which is not preserved. So we say that those symmetries, like the fourfold rotation that are preserved, and they are collectively form the simulation group. So all of the symmetries of the pattern that map this fragment to itself are reflected in the simulation group talking about what the stabilizer of this fragment does. But there will also be automorphisms of this fragment that are not preserved. And we say, well, we call them broken because that's what everyone else calls them. So we have two things that we're keeping track of. We have the symmetries of the pattern, the symmetries of the motif, and then we have broken symmetries inside the motif. Okay. One thing is, this is something that actually I think more of crystallographers, but I think art historians see this as well. This motif actually does not cover this pattern. We actually have, here's another motif. These two together cover this pattern. So you can have multiple motifs that cover the pattern. So we can have several competing motifs. Notice, incidentally, that this thing will not have broken symmetries because this is one of these irregular pentagons that Marjorie was talking about last time. Now, a motif can actually have several patterns associated with it. So here is a pattern that this motif, all of these are fragments associated with this motif. All of these are fragments associated with this motif. And notice that the simulation group with respect to this pattern is different from the simulation group with respect to this pattern. And you can stack motifs on top of each other. So this is this is probably four or five atoms that are forming this particular square, and you can map this square into this molecular, into this essentially unit cell. And then this is another molecular building block, and that is essentially a ligand. So these are essentially the molecular building blocks, the ligands, and you glue them together to make this unit cell. And then you can put together these unit cells to make this larger pattern. And you can have things of relatively higher height. I have this book that Berthold told me about, Crystallography of Modular Materials by Ferraris, Makovicki, and Merlino. And most of their hierarchies, most of their modularity is essentially height 2 or 3. But you can have heights of several things, and you could actually have motifs that are larger than unit cells. If you look at some of the aluminum silicate articles that have been appearing lately, you could actually have motifs that are essentially entire rods that are then mapped into the structure. In category theory, you can do an awful lot of stuff, provided you don't break the rules. You have to be careful about breaking the rules. So that's it for what I wanted to say about hierarchies. And there are other things, and so these are putting things together. But there's another view, and that sometimes you want to analyze an entire crystal structure and figure out what's going on. So let me take a few minutes to talk about that. So now we don't have much of a vocabulary. Feel free to badger Berthold and me about the terms we just made up. Lowerarchy is actually a word that was invented by C.S. Lewis. There is a heavenly hierarchy and therefore a diabolic lowerarchy. But at any rate, it seemed to be a reasonable terms to use. Of course, the category theorists would talk about co-hierarchies of co-motifs with co-sketches, but we decided, that would be wrong. At any rate, so we have monics, and the situation with a monic is that if you compose it on the right with two different morphisms and yet get the same thing, that means that those two different morphisms must be the same. So what we do in epics is we go the other way around. If you compose on the right-hand side with two different morphisms and get the same thing, that implies that those two different morphisms must have been the same. So now we have a pattern, and we are using a whole bunch of epics, think of onto functions, heading in the other direction. So we have a pattern, and now we have what's called a quotient. And so we have an epic, and it's mapping a pattern onto some other thing, which is the quotient. But again, the problem with quotients is that they don't explicitly represent all the symmetries that are involved. So we want to expand on this construction to represent the symmetries. So the proposal is that instead of using the word cofragment, we use the word sketch, because in a sense, you are producing a sketch of the pattern. And so it's essentially reversing all the arrows for a fragment. Now we're mapping from the pattern onto the quotient, but also all of the symmetries of the pattern are preserved in the quotient. But we do have a co-simulation group of all of the symmetries that are preserved by the map, but we also have a whole bunch of symmetries of this thing that are not preserved. And I drew a picture here to say you can have multiple different sketches that map into the same album. So an album is essentially a collection of all of these different sketches. Now, we can get different kinds of albums from the same pattern. And it depends on what you want to do. This is essentially a unit cell of this thing. And of course, when you want to look things up in the tables, IUCR tables, you're looking for these unit cells. But suppose you want to stand back and say, this thing is very, very cluttered. I want to simplify it so that I can see what I'm looking at. So what this does is it takes this entire fragment and it maps it to a single vertex. This entire fragment is mapped to a single vertex. And that means you have collections of 4 ligands mapped to single edges right here. So you get a simplification so that you can see the thing more clearly. And these simplifications can be helpful when you can see pseudo-symmetries. I understand that that's the word. So here we have essentially something that looks like the SQL two-dimensional graph, but it has all of these weird things surrounding each one of the vertices. Now we can contract these square shapes, and using the continuous map, this is the continuous topological model category of graphs. So we contract this entire piece here into a purple dot, this entire orange piece and all these blue pieces into this brown dot, and we get alternating brown and blue dots so that we might be able to see this thing more clearly. And you'll notice that now we are introducing some symmetries, because right here, there is no reflection across this blue line, but now there is a reflection across blue lines right here. So going from the pattern here to this sketch, you introduced symmetries, which when you try to go backwards are broken. On the other hand, every single symmetry of this pattern here is preserved in this pattern over here. And you can keep on going. Suppose you don't care about these colors. Now you get a nice black pattern, and all the vertices are the same. And so this is indeed your old friend SQL with all of the symmetries of SQL. And you could say that the symmetries that are not reflected going back towards the pattern, we're not interested in. We are interested for the moment just in the symmetries of this pattern right here. So that is another thing in these hierarchies of sketches that you can deal with. There's another thing that you can do with the sketches, and now I'm switching. You have to keep track of which category of graphs you're dealing with. So I was just a moment ago, I was talking about the category of graphs treated as topological spaces with continuous functions. Now I'm turning around and I'm talking about the category of graphs with the incidence relation where edges are simple primitive objects. And now I'm saying here, I have a way of describing, and I think I've inflicted on this on at a previous MACSMIN, I have a way of parametrizing a whole bunch of graphs that look like diamond. And the thing is that the actual graph that I get, that this thing represents, is a symbolic object. And various projections of that symbolic object, I produce these things. What I have is a symbolic object with a whole bunch of variables, and I plug in values into those variables, and I get this thing. Or I plug in different values into variables, and I get this thing. Or I plug even different values into variables, and I get this thing. These are all isomorphic to the diamond lattice, but I can plug in values, and I can get this thing, which is two-dimensional. I flattened the diamond. Or this thing, or even a rod. And the point is that what I have in this category is this abstract symbolic thing full of variables. And then when I plug in particular values, this is another way, morphism. There's no law saying I can't create a morphism by plugging in values. It still obeys the rules. So as long as I obey the rules, I can have it be a category. And the thing is that diamond is rather simple-minded, but I can deal with more complicated symbolic structures, and I can get some interesting things. So for instance, there is a 5-dimensional crystal net. And by that, I mean, it is a symbolic periodic structure with a lattice group of dimension 5. But it has only 3 variables. I plug in into those 3 variables 3, 2, 2, and I get this thing. And it is called borosite in the RCSL database. Or I can plug in this variable and I can get CTN, that's this thing. Or I can plug in 3, 2, 1 and I can get this thing. So what I have here is technically a pattern. It's actually a 5-dimensional lattice, and it has morphisms that send it to 3 different motifs. And so this is a way of saying these three crystal nets are related in the sense that they came from the same 5-dimensional crystal net. So this may provide a way of classifying crystals in a way that may be meaningful. At the moment, I don't know what the chemical, physical, material consequences of coming from the same 5-dimensional crystal net might be, but I wouldn't be surprised if there was something. After all, quantum mechanics is all linear algebra, and this is linear algebra, so maybe there's something of significance to it. And then, of course, you exclude the entire thing together. You have the hierarchy over here, the lower hierarchy over here. And just because the morphisms are defined differently doesn't mean that as long as they compose, this is perfectly legal. So that's a brief description of category theory. One difficulty with category theory for crystallographers is that there is no immediate source to category theory for crystallographers. David Spivak actually wrote a book called Category Theory for Scientists, but that is actually a category theory book for software engineers who write software for scientists, which is not exactly the same thing. But Bertold and I are writing stuff up, and we intend to produce a sequence of things on what's going on with category theory. So that is introduction to what some people have long called, and some people still call, abstract nonsense, but we do hope that it will be helpful. And so are there any questions, comments, criticism?
Thank you very much, Greg. Let me stop like